There we go. Is my sound good?
Yeah, you sound good.
Right on. I just always feel a need to check because sometimes it just doesn't work. Cool. Well, I realize my air conditioner is not on. I'll be right back. There we go. How's everyone feeling?
Good for the most part.
That's good.
I'm mainly just stressed about what I got on the test.
So there's you don't need to stress, and we'll talk about why. And there's also we'll also talk about things you can do to get better for the next one.
Yeah, I was gonna come to your office hours to talk about it, but I see we're going to talk about it in class. So
yeah. So I mean, we're not going to talk about every question because we don't have time to do that. But
no, of course.
I'm going to talk about the ones that that more people got wrong than right, which is actually only a few, which is good. But I'm going to hold off. I'm going to wait until 2 to start talking about that, just because, yeah, I don't want to be repetitive for the people who are
I get it.
already.
I get it.
My cat was asleep on top of my printer earlier, which is under my desk, but she seems to have moved, so that's probably good for the sake of interruption. So I was kind of surprised that, so I have a 10-month-old kitten, and I guess she's almost 11 months old now, but she likes to jump on my desk in front of the computer, so I'm actually very surprised she has not done that during our class yet. But I do apologize if she does. I also apologize if you get a bunch of like random letters in an email because she, so I was sending an email to one of you yesterday and she jumped on the keyboard right as I hit send. So if you ever get an email that is like mostly coherent but then has a bunch of random letters in it somewhere, that was the cat jumping on the keyboard before, like right after I hit send, but before it actually sent. So.
Show us the kitten. Do a kitten reveal.
I don't want to wake her up because
that's fair.
If I wake her up, she will get in the way. But at some point, I'm sure you'll see her.
Okay, make that a promise.
Surprised she's not like, oh, they're talking about me. I'll come here. All right, so it's 2. So let's get started. What we're going to do today is we're going to first talk a little bit about the test and how it went and why you shouldn't be worried. And then we're going to talk about rocks. And we're going to introduce, I mean, I feel like, yeah, this is geology class. We're going to talk about rocks. But we're actually going to introduce some of the major groups of rocks and some major concepts about rocks that are going to stick with us for the rest of the semester. If you were expecting this class to just be talking about rocks, well, now your time has come. But yeah, I'm guessing that's not going to take the whole class because it's just an introduction. And so at the very beginning, when we talk about the test, I'm going to talk about some of the questions that more people got right or more people got wrong than right, which is actually only a few. But then with the time that's left at the end, if people want to go over other test questions, we can. But I'm going to also ask you to sort of, if you have questions about specific questions on the test. Oh my God, why is my phone ringing so many times? Let's turn that off. Okay, then if you have questions about specific questions, I'm going to ask you to hold on to those until the end, and hopefully we'll get there. But yeah, first of all, how are y'all feeling?
Good.
It's good. Was it worth all those F's in the chat, do you think?
Yeah.
It was worth the F.
No, because I for sure didn't get that.
The what? Sorry?
I said no because I did okay.
Yeah. So I think in general, I was actually really happy with how this went. Yeah. And so as I was saying kind of quickly at the end, like when I'm writing a test, I'm not trying to trick you. Like sometimes I'll write some questions that are deliberately harder than the others, but I'm never going to be trying to trick you. I just want to see what you remember of the major concepts and how good you are at applying them to things. And so the average score on this test was a 70, which is a C, which is awesome. Like ideally, like, you know, your average should be a C or higher, but usually C is defined as kind of the average. And so I'm really happy with that. And especially if you look at this distribution, you'll notice that actually more, so this is it's a histogram. So each of these is a point, like so 70, 71, 72, and so on. And this is the number of people who got that grade. And so if you notice, actually more people got above 70. And it's just that the average is kind of lower, partly because there were some pretty low scores, a couple of them, and there were also 2 people who actually just didn't take the test, and it factors their zeros into the average. So in reality, the average is actually higher than 70, and I think that's really awesome. Like a lot of people got like an 85, which is like a really solid grade, and that's awesome. So I'm happy with this, and especially I think a lot of this was, you know, the first time you're hearing this stuff. But over the course of the semester, all of the stuff that we talked about for this first test is going to come back again and again and again in different contexts. And so it's not going to be unfamiliar anymore. And so in general, like the last time I taught this class, people did better on each successive test. So I think it's only going to go up from here, especially if you continue to stay as on top of the vocab and the quick quizzes and the stuff that you've been doing well on so far. But yeah, I think this is really solid. I think I do want to mention though, is so this average time counts, it's timing everyone because there's a 45-minute limit on the test. And the average time was just about 33 minutes. And I'm going to strongly recommend that you use like the whole time. Even if you think you've finished answering everything, look at it again. Make sure you didn't miss the word not or doesn't. Because I think there were a few questions where I think some people missed the word not or doesn't. Make sure there isn't an all of the above. Like definitely don't just pick the first one that looks right and stop, because there might be an all of the above or like a just A and C, or like, you know, there might be multiple options. So make sure you really read everything, look at it again, make sure you didn't just click the wrong one. Because I will say that everyone who got over 50 points on this test took more than half an hour to do the test. Like all of the scores above 50 were people who took more than 30 minutes. So, I mean, there were people who did well that took a very short amount of time because they were, you know, really good at the material. There were also people that that did pretty badly and took a long time because they maybe didn't study as well, but that's what we're going to talk about, is things to do. So Diana says, will topics on this test come up on future tests? Yes, but not directly. So I'm not going to just straight up ask you like, what is a mineral? on the next test, for example. But in order to understand things about igneous rocks, you're going to have to understand stuff about silicate minerals. And so that's going to be really important. So all of this stuff is going to come back in new contexts and new ways. And so we'll readdress everything. Like, we're not going to like never talk about silicates again. Like, I'm going to introduce that stuff again. But it's all going to come back just in the context of new things. So everything, like this first test was about building blocks. It was about literal structural and chemical building blocks of the Earth. And so in order to understand the details, you need to know the building blocks. So it's going to come back, but I'm never going to ask you like the exact same question on 2 tests, if that makes sense. Does that answer your question? And the final exam is not multiple choice. The final exam is going to be open notes, open book, open canvas, sort of interpretive problem solving kind of questions that's really going to show synthesizing things. So that could be anything is fair game. But we'll talk more about the final way later. But yeah, I was really happy with how this test went. And but if you are not happy with how this test went, do not panic. There is no reason to panic. First of all, it was the first test. All of this stuff is new. As I was saying, like, as you hear more of it for the rest of the semester, it's going to become more and more familiar and more easy for you to remember and use. So you'll just get better at it by being exposed to it, especially if you keep coming to class and doing all the work like you've been doing. But still, these tests, first of all, all 4 of them together are only worth 30% of your grade. So the biggest percentage of your grade is just the things like the quick quizzes and the vocab, and just those things are worth the most. So stay on top of them, and that's really important. But the tests are only worth 30%, and there are 3 more of them. And the lowest one goes away at the end of the semester. So I have a policy where, like, no questions asked, your lowest test grade disappears at the end of the semester. So like, if you're one of the people who didn't take the test, don't worry about it. Just make sure that you take the other 3. Or like, if you just, let's just say you really, really, really don't understand sedimentary rocks and you get a much lower grade on that test than the other 3, then the sedimentary rocks one disappears. So it's going to take your top 3 out of 4. And also, there's going to be more extra credit later. So there will be a couple of short extra credit questions like there was this time on each test. And they'll all be worth about like 5% of the test grade. But there's also going to be 2 sort of bigger extra credit assignments. So I'll give the first one after the second test and the second one after the 4th test, or around the time of the 4th test. Or maybe, yeah, probably then. Those will be worth more points. And so you'll have options to make up for things. But really the most important thing, though, is if you're worried and unhappy about how you did, is to come and ask questions. The best way to do better next time and to get more points next time is to learn about what you got wrong and where your thinking went off and make sure that you're in better shape for next time. And so you can always ask me questions. You can always email me questions. You can always come to my office hours. They're on Tuesdays from 2 to 4. You don't have to make an appointment. Just show up at that Zoom link. And if you can't do Tuesdays from 2 to 4, but still want to talk on Zoom, just send me an email and we can try to schedule another time. I'm always happy to go through this stuff with you. And coming to office hours really works. So the first time I taught this class, there were some people who got like 45% on the first test. And they started to come to office hours, and they came to office hours really regularly, and they ended up getting a B+ in the class. They ended up doing really well because they came and asked questions about, you know, what did I do wrong, but also like, am I understanding this right? Like, it's totally okay to say, hey, can I describe this to you and make sure I understand it? Like, I'm happy to take all of those kinds of questions in office hours, over email, on Zoom. And if there's time at the end of class. If you have a really long question, I mean, I will keep trying to get at all of your questions during class. But if it's a really long question, it might have to wait till the end, but I promise I am always happy to answer questions. And I would much, much, much rather like talk about things as soon as they've happened than later on, just because it's, first of all, it's fresher, but also the sooner you come to understand things, the more it'll help you out later. Again, I'm here to help you. I want you to do well in this class. I would love to be able to give, like, I would love for the average test grade to be a 95. That would be awesome. And so just, I'm here to help you, but like definitely come and ask, you know, read the book, look back over the vocabulary before the test, look at the quick quizzes, like they have explanations of all of the answers if you go back and look at them. So definitely use everything you can. And, but again, I'm really happy with how it went, and I don't think any of you have anything to worry about yet, just so long as you keep coming to class and doing the work. But just any like general logistical, like not specific to certain questions on the test questions right now. All right. So I'm going to go through a couple of the specific questions. So there were actually only 3 questions that most people got wrong. The other 27, most people got right, which is awesome. And actually the 3 that most people got wrong were, I think, some of the hardest questions. So that's good. Like, some of the questions are deliberately harder, and so it's fine. But we're going to go through those 3. And then there's another one where it was pretty close to 50-50 that I'm going to talk about before we get on to talking about rocks. But yeah. So the first question that most people missed was this one, which is which of the following is an example of an absolute age? And so again, an absolute age is a thing like there is a specific time, a specific date. And so the second most voted for, the second most chosen answer was in the 1860s, which is the correct answer, because that's in a time. The 1860s is a time. It's a specific time. Before the turn of the century, most people didn't choose that, which is good, because it's before something. It's before a general thing. It doesn't have any open-ended, it's very open-ended. It's not like this is the range that it happened in. And similarly, after the Great San Francisco earthquake of 1906, like that's a specific thing with a specific date. But again, it's just after that it could have been 1907, it could be 2020, it could be 2030. But the thing that made this hard, and I was fully expecting that some people would pick this wrong answer, is the one that's 100 years ago. Because if you think about that, yeah, 100 years ago was 1920, but that's only 100 years ago in 2020. If, let's say you were reading a book that was written in 1990, then 100 years ago is 1890. So 100 years ago is relative to now. It's not, so even though you might think of a specific date, you know, 100 years ago changes, like the specific date changes every year. So that's why it's a relative age. It's just relative to now. So does that make sense? And I did mean for this to be one of the harder questions, so don't feel bad if you missed this. The next one that more people missed was this one. This is a diagram, and it says we have a boundary between 2 oceanic plates. And it says, what kind of boundary is the middle section indicated with the bold line? And so I was talking about this line, not these guys, but this middle line. And so I think a lot of you just said, oh, mid-ocean ridges are divergent, which is correct, but I'm not asking about the mid-ocean ridges. I'm asking about this line. And so the hint is to draw things. So like, we know mid-ocean ridges are divergent boundaries. Yeah, and a lot of people got all those questions about what mid-ocean ridges are right. And so the trick is to think about, okay, if this is a divergent boundary, how is it moving? Divergent means it's moving apart. So if you were going to draw the way the plates are moving, you would have that one going this way and that one going this way, because things move away from the mid-ocean ridge. But now that you've done that, you've got these arrows, right? And so if you're gonna, now let's take these arrows and move them over. Like this whole area is moving this way, and this whole area is moving that way. So you can definitely move these arrows next to the other plate boundary. And so what kind of plate boundary is where you have things sliding past each other?
A transform.
Yeah, and so most of you did say this was a transform boundary. But the way to tell what kind it is to look at the way the arrows are. So yeah, you might look at just this boundary itself and go, yeah, this mid-ocean ridge is to the right of the other mid-ocean ridge, so it's moved to the right. Yeah, so this is why this was hard. Yeah, so Anna's saying, I think I got confused between right and left lateral. But yeah, that is why this is a hard question. So it's okay if you got that wrong. Again, this is one of the ones that I knew was harder. Yeah, so you need to draw those arrows and think about which way are the arrows pointing. So like, let's say you're standing over here and looking that way, then the arrow points to the left. But also if you're standing over here and looking that way, this arrow also points to the left. So does that make sense?
Yeah.
So this is this was meant to be a sort of trickier, multi-part kind of question that you had to think about how things are moving. But yeah, so when it comes to transforms, you want to, yeah, it's the one across from you. Yeah, so you want to think about which side are you standing on and which way did the other side move. And so like it's tricky because yeah, it looks like the ridge is to the right, but the ridge is the thing that's doing the moving, not the thing that has been moved. Does that make sense? With continental transforms, it's a lot more straightforward. So like if you had a continental transform and you had, say you had a continental transform, because those aren't driven by ridges, the way things are gonna get offset is the way things are moving. So like if you had the plates moving this way on your continental transform, then if something were to cross it, like let's say there were a road and then that boundary moved, the road would get offset like this. So, but in this case, the road isn't what's driving the boundary. It's just the thing that's getting moved. But in the oceanic ones, the ridges are driving the boundary. So this is doing the moving and that is being moved. So is that still clear-ish? This is gonna come back kind of at the very end of the class when we talk about earthquakes. We're not gonna worry too much about this before then, but it's gonna come back a lot when we talk about earthquakes. So you got time to figure this one out. So any more questions about this question? And just as a heads up, a thing I might very well ask you on the final is I might give you a diagram of some plates and tell you how some of them are moving and ask you to think about which way the other ones must be moving based on that. So just kind of keep that in the back of your head that that is something I could ask you. But yeah, moving on. The next one that most people missed was this one. And so this one uses all of those principles we talked about in like the second day of class. So it was a pretty long time ago. But it uses those principles of basically, I mean, it uses some of the layering principles and the cross-cutting principles. And also the idea of just something has to be there in order for something to happen to it. And so the correct answer is that the limestone, oh wait. No, you know what? I put the wrong one. Yeah, this is the correct answer. I'm gonna go regrade the test. I misread my own test. So this is the correct answer you were about to say. If you ever see something like that and I just look super wrong, call me out. This is correct. And the reason this is correct is, I think I switched this from last time. I used to have it the other way. Yeah, so something has to happen in order for something to happen to it. So yes, limestone formed first is the oldest. Yellow sandstone formed on top, red sandstone formed on top, basalt cut through. Yes, this is correct. I am sorry. I'm gonna go and fix it right after this class. So for those of you, for 48% of you, you're gonna get another 2 points. So that's gonna shove the average up. What was I thinking? I made a typo. That's what I was thinking. We're not machines. Yeah, so that, yeah, cool. So I will fix that. But yes, this is good. Cool. Yeah. Moving on then. So this one most people got right, but I still want to talk about it because it was close. I mean, I kind of deserve to be dragged for that. I mean, I was about to say most of you missed that, and then most of you got it right. But anyway, this one is tricky because it is again that principle of I'm messing with you. It's fine. This is that principle again of like something has to exist for something to happen to it. And so, in order for something to become included, it has to exist. So, like if something is included in another rock, that means it's surrounded by the other rock. And so something can't be surrounded if it's not already there, basically. And so if it's already there, it's older. Does that make sense? You can have, so now I'm sure some of you were thinking of cases exactly like this, where yeah, the basalt is younger than all of this stuff. But in this case, the basalt cuts all the way through. So the difference between something cross-cutting is like this, it cuts through everything. It's not completely surrounded. It actually cuts through on both ends. So something that's included is completely surrounded by the other rock. So it's just like a chunk of one rock included within the other rock, not something that blasts all the way through. So does that make sense? Yeah. And so we'll talk more about inclusions. We'll talk about it some with igneous rocks, more with sedimentary rocks. But yeah, it's sort of an inclusion is a chunk that's surrounded by other stuff. Whereas like a cross-cutting feature, that's what we'd call this, is something that goes all the way through. Yeah. So yes, there were only 2 questions that most people missed, and one where the professor clicked the wrong button when writing the answer key. So again, this is really good. So with that, does anyone have any questions about these things, these particular questions? All right. In that case, what I'm going to do is we're going to switch gears and talk about rocks now. And I still don't think that's going to take the whole rest of the class. So if you want to go through any more of the specific questions, at the very end, we'll do that. But for now, I'm going to switch to the other PowerPoint. And no, don't stay in pencil mode. That's not helping. Okay. No, stop share. Share screen. Where did it go? Oh, I think I have to exit. This is being annoying. Hold on. There we go. Okay, are you seeing rocks versus minerals now?
Yes.
Okay, so it's not randomly showing you my other class again.
No, it's not.
Okay, good. All right, so we ended with minerals last time, and I think we also kind of talked about the idea how a lot of times, especially if your only geology class was in like elementary school, they talk about rocks and minerals together. And of course, they're related things. They are very much related things. You cannot have rocks without minerals, but they're different. And so if we go back to our definition of a mineral, and hopefully by the time I've showed you this slide a million times, although you all did really well in the questions about what is a mineral. But if you remember, a mineral is naturally occurring solid crystalline material formed by geological processes that has a definable chemical composition. And when I introduced minerals, I said that they were the building blocks of rocks. And so now I'm going to finally give you a new definition slide that you're going to keep seeing again and again as well. And that definition slide is for a rock. So a rock is a coherent, naturally occurring solid, and it consists of an aggregate of minerals or sometimes a body of glass. So let's walk through that step by step. it is coherent. It has to be stuck together as a solid unit. So sand is particles, but if sand is not, the difference between sand and sandstone is that the sand is individual grains that aren't stuck together, and a sandstone is those grains have become cemented together into a rock. So it has to be coherent. If you break it up enough, it stops being a rock and starts being sediment or particles or grains rather than rock. It is naturally occurring. Again, just like with minerals, it has to occur in nature. If it occurs in a setting that is only made by people, only in a lab, it's not really a rock. Like asphalt is not really a rock because it's only created in artificial things, even though it is coherent, consists of minerals, and is solid. But if it's only made by people or only made by living things, well, I guess only made by people, really. It has to, I guess, or only made by living things. It is not a rock. It has to occur in geological processes in nature on its own, not engineered, not deliberately created. Solid, I think that one's pretty self-explanatory. If it's liquid, it's not a rock. That said, just as a little bit of a semantic thing, we'll often talk about liquid rock when we're talking about igneous rocks in particular. So lava is liquid rock. But technically, like by the really, really strict definition, it's not a rock yet because it's liquid. It has all of the minerals in it that as soon as it hardens, it becomes a rock. But technically, it's because it's liquid, it's not a rock yet. But that said, like, you can still use the term liquid rock. We're going to talk about molten rock, liquid rock, melting rock a lot in the next few weeks. So don't worry too much about that one. But in general, and I mean, the stuff we're going to be talking about is solid. But that's just part of the definition. So the next one is an aggregate of minerals. So an aggregate just means a collection. It's a bunch of minerals stuck together. So if you remember, minerals have set chemical formulas, but rocks don't. So like quartz is always going to be SiO2. But for any given rock, you're not going to have a chemical formula that's always in that rock. In general, you're going to have, well, for some rocks, there's going to be kind of a balance of different minerals that make up that rock. So like a rock that has, like if a rock has a whole lot of quartz in it, it can never be basalt, for example. Or if a rock is made mostly of metal, it's never going to be calcite, just because of the kind of minerals in it. So there are some rules, but it's not as really hard and fast as like every mineral has a chemical formula. And for some rocks, the chemical stuff matters a lot. For some of it, like for igneous rocks, it matters a lot. For some rocks, like sedimentary rocks, it doesn't matter that much at all. So we'll talk about that on a case-by-case basis. And that last thing, a body of glass. So that's kind of a special case because if you remember, glass is not a mineral. Glass does not have crystals. And so sometimes, natural glass forms usually in volcanic settings where something gets launched out of somewhere really hot into somewhere really cold so fast that it can't form crystals. And so in that case, again, you have all of the chemicals required to make minerals. They just cooled too quickly to meet the definition of a mineral because they didn't form crystals. So in that case, you can technically, in this way, the rock is not made of minerals, although it's made of the same chemicals that could be minerals if they'd taken the time to form crystals. But we're not going to talk about glass a lot in this class. Basically, we'll talk about it a little bit when we talk about volcanoes the week after next. But for the most part, we're going to be just talking about coherent, naturally occurring solids that are aggregates of minerals. So does that all make sense? Any questions about any of those parts of the definition? Cool. All right. Sometimes it's kind of weird to like, yeah, I know what a rock is. And then when you think about like, oh, this is the actual definition. It's like, yeah, I mean, I guess that describes the thing I already knew about, but in ways you didn't necessarily think about it. Oh yeah, also worth noting, some rocks are an aggregate of just one kind of mineral, but that's fairly uncommon. We'll get to that later. But yeah, so there are three groups of rocks. There are three major groups of rocks. Does anyone remember what these are?
Is it sedimentary, metamorphic, and igneous?
Exactly. Yeah. So those are the three. So how was that? Hopefully those are words you're all familiar with from the vocab, but also from probably fourth grade or the Magic School Bus or Bill Nye the Science Guy or something. Has anyone not heard of those before? Is Bill Nye the Science Guy still on? I don't think he is. Okay. But yeah, so igneous, sedimentary, and metamorphic rocks are our three groups. And that's kind of how we're going to be structuring the rest of the class, is based around these groups. So igneous rocks are formed by solidification of molten rock. So there's that word again, molten rock. It's a little bit of a contradiction, but it's basically stuff that was liquid and then it hardens into a rock. So if it started as lava or magma, and we'll talk about the differences in those next week. If it started as lava or magma and it hardens into a rock, that is an igneous rock. Igneous comes from the word ignis, which means fire or heat. So those come out of volcanoes or are sometimes in the ground under volcanoes, basically. Then sedimentary rocks, we already talked some about those when we talked about our layers. They're formed by fragments of material that have gotten cemented together. So by stuff that has piled up and gotten stuck together by something. So like imagine again, a pile of papers on your desk and then you spill your coffee and the papers get stuck together. Or by precipitation from solution. So if you remember when we were talking about minerals, how sometimes you can precipitate minerals out of a liquid and form a solid. And so you can get some rocks that form in that way. And that's a group called evaporites. And we'll talk more about those in several weeks. And then the last group is metamorphic rocks. And so that comes from metamorphosis, from change. And so but metamorphic rocks, by definition, started as some kind of other rock, and that they either change their structure or their chemical composition due to changes in pressure, temperature, or surrounding chemistry. So if you squeeze it real hard or heat it in a way that it doesn't melt but still changes, or add some other stuff to it, it can turn from one kind of rock into another. And this is the order that we're going to talk about these in this class, by the way. So what we're going to do is we're going to, for the next week, we're going to talk about igneous rocks. The week after that, we're going to talk about volcanoes, because that's what forms them. And then there's another test after that, and then a holiday. Then after that, we're going to talk about sedimentary rocks, and then a bunch of things that form them. So we're going to talk about rivers and floods and glaciers and landslides when we talk about sedimentary rocks. And then lastly, because you can't talk about metamorphic rocks without understanding the other two, the last part of our class, we're going to talk about metamorphic rocks and the tectonic settings that make them, and things like mountain building and earthquakes and big collision forces and all kinds of forces that can lead to rocks turning into other rocks. So that's the structure of the rest of our class. And so there will be a test after each of these things. And they'll all build on each other. So and these also kind of go in the order of complexity. Igneous rocks are the least complex and metamorphic are the most. So we're also going in that order for a reason. But just by way of a little bit more detail. So igneous rocks, they form from solidification of molten rock. And they form in association with volcanoes. So this picture, this is Hawaii. A lot of people take pictures of this. And this is a rock that came out of a volcano and solidified. But you can also have some rock that never actually erupts and it just cools under the volcano in the ground. And so those are all igneous rocks, and we'll talk about both of those. And so with igneous rocks, the chemical composition is the most defining trait. There's definitely some stuff about texture, but there's really kind of only two textures. Well, three if you count glass. But there's really only two major textures of igneous rocks. And it's all about the minerals. And in this case, that's where all of those silica structure things that we talked about at the very end of the last unit is really going to come into play. So all of that stuff about tetrahedra and different structures, that controls everything about igneous rocks and about the volcanoes that made them. And actually, believe it or not, and we'll talk about why, the way those little tetrahedra fit together directly relates to how explosive a volcano is. So explosiveness ties back to mineral structure. And so big explosions or not is kind of one of the last things we're going to talk about before the next test, but there will be boom. So any questions about general igneous rock traits? Cool. And next, sedimentary rocks are formed by fragments of material that have become cemented together or precipitated from solutions. And so this picture is Rainbow Basin. This is in Eastern California. Not actually that far from here. I think this is about a little less than 2 hours from here, maybe. And so sedimentary rocks form from sediment. And so sediment is just stuff, it's particles, it's stuff that's not stuck together. And they form where sediment piles up and gets stuck together. So these really, a lot of them form in association with water, with lakes and rivers and oceans. So this, a lot of the stuff at Rainbow Basin used to be underwater, and now it's not. Now it's the desert. But a lot of them form in association with water, sometimes at the bottom of hills. And with sedimentary rocks, it actually doesn't matter that much what the chemicals are in them, for the most part. I mean, sometimes it matters. Like the ones that form from evaporation, it's kind of all about the chemistry. But for the most part, the way that these things have become stuck together and the shape and size of the different chunks in them and the stuff that's holding those pieces together are really what are important for describing sedimentary rocks. And these things tell us about the environment in which the rock formed. They tell us both about how those chunks got separated from other rocks and then how they got stuck together again. And of course, these are also the most important rocks for taking apart the history of the Earth. Like this is why all of that uniformitarianism stuff, all of that cross-cutting relations and things are tied up in sedimentary rocks, because you have these layers that just form on top of each other in certain environments. And so really these are, you know, and there's a lot of sedimentary rocks. They're very, very common in many places around the world. And this is also where fossils end up. So these are really important for Earth history, both in terms of just telling us what happened in that spot and in helping us understand the sequence of events for the whole planet. And so unfortunately, just with the length of this class, we're not really going to talk about fossils in here, but there are whole other classes on that. I think Geology 103 is Life on Earth. There's a Life on Earth class. There's also an upper division Gen Ed, I forget, 300 and something, that's about dinosaurs, if you're specifically interested in dinosaurs. But we're not really going to get into the fossils here, even though those exist in sedimentary rocks. They're like some of the stuff that piles up and gets stuck together. If it melts into an igneous rock, it's gone. And then, so any sedimentary rock questions for now? And then the last kind are metamorphic rocks. And so they form, again, when pre-existing rocks succumb to high heat and high pressure, and sometimes a change in chemistry, and they turn from one kind of rock into another. And those are defined both by their chemical composition and their structure. So sometimes the metamorphic change is just that the structure of the rock changes, but the chemicals stay the same. And sometimes the structure remains relatively unchanged, but the chemistry changes. Sometimes it's both. So this is a kind of rock called gneiss, G-N-E-I-S-S. And it's a kind of thing where it can start as either an igneous rock or a sedimentary rock. And the amount of pressure involved here just makes the minerals reorganize themselves. So rather than being all mixed up, they form into these bands of light and dark. And, but sometimes you can have minerals turn into totally different minerals. So metamorphic rocks are really complicated, but they're also what tell us so much about how plate tectonics has changed in a given space. Because if we remember when we talked about plate boundaries, like we talked about the Appalachian Mountains, right? So they formed as a convergent boundary when two plates came together. But then there was a divergent boundary as then the Americas and Africa and Europe split apart. And now they're not a plate boundary at all because the boundary is in the middle of the Atlantic. So things can be at different plate boundaries, and different kinds of plate boundaries create different kinds of rocks. And actually most metamorphic rocks tend to form at plate boundaries because that's where the high temperature and high pressure is. So these rocks tell us about the conditions in which they formed. And so we'll be talking about those last. Any questions about metamorphic rocks? By the way, our state rock in California is called serpentinite, and it is a metamorphic rock. And it's a kind of metamorphic rock that forms in subduction zones, but then something has to happen to launch it out of the subduction zone and onto the continental plate. So it's pretty wild. And it tells us a lot about how California formed. But again, I keep mentioning California because we're here and there's a lot of good examples here. Not going to talk a whole lot about California by itself in this class because again, this is 101. It's about the whole Earth. But if you're interested in California's geology specifically, then I'm probably teaching Geology 344 in the spring, which is called California Geology. So it's specifically about here. But yeah, anyway. So moving on, so we describe rocks. I mean, there's these three major categories, but we still describe all rocks regardless of what category they're in based on four major criteria. So we can talk about its texture, we can talk about its grain shape or size, its chemical composition, and whether or not it has layers. Because all of these things are useful in learning things about the specific kind of rock and then learning things about the environment that formed them. So a lot of these are not as nitpicky as the mineral ones. So you're not going to do a scratch test on a rock to see how hard it is because it's going to have a lot of different minerals in it. And similarly, like rocks don't have cleavage because they have a bunch of different minerals in them that behave in different ways. Or the same, you can't do a streak test because they have different minerals in them. It would depend on which mineral you're streaking. So a lot of these things are they're a lot more qualitative, honestly. They're pretty qualitative, but still useful. So texture, in general, we talk about two major kinds of textures. So a crystalline rock is made of crystals. It's a rock where you have different crystals of different minerals interlocked together. And those form when the crystals actually form next to each other and just stick together as they formed. So this is an igneous rock. This is actually granite. And can you see how there's some pink stuff and some white stuff and some black stuff and some gray stuff all together in this rock? Well, those are different crystals of different minerals. And they all formed together as this rock cooled from a liquid. And they just formed and just stuck together. So this rock formed like this. And you're not going to be able to separate these crystals from each other very easily. And even then, like if you smashed this, you probably wouldn't separate the crystals from each other. You'd just make a mess. The other major texture is called a clastic rock. So a clast is another name for like a little grain or a little particle. So clastic rocks are grains of different minerals that are bonded, or chunks of different rocks that are bonded together by a cement of a mineral. And so in this case, the grains form separately and get stuck together later. So like in this example, like in the granite, all of this stuff formed at the same time. This is a sedimentary rock called a breccia. Don't worry about that name yet. We'll get back to that. But all of these chunky fragments formed in one way. And then all of this darker stuff that has them stuck together formed in a different way and then stuck them together. And so that is, so these things we would call, these big chunks we'd call clasts, and this dark stuff we'd call cement. But sometimes the clasts are really tiny. Sometimes you can't really see the distinction between the clasts and the cement. But also sometimes in crystalline rocks, you can't necessarily see the different crystals unless you look at it under a microscope. So it's just a fundamental difference in how they form. So most igneous rocks are crystalline. Most sedimentary rocks are clastic. Metamorphic rocks, it's fair game. Metamorphic rocks are whatever they want to be. So any questions about that? Cool. All right, then the next big one is the grain shape, or the grain or crystal shape or size. So whether it's a crystalline rock or a clastic rock, the size of the crystals or the grains tells us a lot about what's going on. And so for different crystal sizes, so in crystalline rocks, bigger crystals means that the rock took a longer time to cool. So these two rocks are actually, they have the same chemical composition. This is called granite, this is called rhyolite. They're both igneous. But the difference here is that this granite took a long time to cool, and so the crystals had a long time to grow, whereas this rhyolite cooled very quickly, and so the crystals are really, really tiny. In terms of clastic rocks, the grain size tells us, and shape, but especially size, tells us how much the source stuff got pulverized before it became a rock. So this is, again, a breccia. This is called a conglomerate. Again, don't worry about that for now. They're both sedimentary. But in this case, you can see these are bigger chunks and these are smaller chunks. Basically, the bigger the chunks, the less something has been broken apart before it got stuck back together. And also the more powerful the thing that broke it apart. But another thing that's important, especially with clastic rocks, but sometimes in crystalline rocks, is how sharp versus how rounded the edges are. So like in this piece of breccia, all of these edges are really sharp. And in this conglomerate, these things are a lot more rounded. So that also tells us, like, you know, these component clasts probably got tumbled around a lot before they got stuck together. Whereas these chunky ones probably broke pretty abruptly and then got stuck together pretty quickly. So just looking at shape and size are really important for all kinds of rocks. Although kind of a little bit less with metamorphic rocks, but again, we'll get there. That's why we're doing metamorphic rocks last. Any questions about this? Wait. One more minute. What am I waiting? One more minute for the slide. Okay. And I will put this slideshow up right after class. So this is going to go on Canvas immediately because this is only one lecture. And again, just to remind, like, I always put the slides up, but like if it's a 2-lecture topic, I'll put up the slides after the second lecture. So like for igneous rocks, it's going to be 2 lectures. So that'll go up after next Wednesday, even though we're going to start talking about it on Monday. Good to go?
Yes, we're good.
So then the next one is the chemical composition. So as I said earlier, rocks don't have chemical formulas. You're not going to be able to say this is the chemical formula for this rock. But sometimes the proportion of the different minerals makes a really big difference. So these are 3 different igneous rocks. They have very much the same texture, kind of the same crystal size. Whoops. They all formed in the same way, all of these. But the difference is how much of which minerals are in there. So like this one is mostly light colored stuff with just a couple of dark things. This one is mostly dark colored stuff with just a couple of light things. This one is a pretty even mix. And so the proportion of different minerals is sometimes a major distinction between what kind of rock you're dealing with. And so that's like the most important distinction for igneous rocks and a very important distinction for metamorphic rocks. But not super important for sedimentary rocks. But like igneous rocks it's all about chemical composition. Like igneous rocks it's all about chemistry. Sedimentary rocks a lot of it is about physics, and metamorphic is both. So any questions on this slide? And you'll be seeing these pictures of these specific rocks a lot. You are going to be very familiar with these rocks by the time of the next test. You will know this is the kind of thing where by the next test, I might show you a picture of one of these and be, what kind of rock is it? Because there's really only a few kinds of igneous rock. Yeah, just as a heads up. So okay to go on for the next slide? Okay, not hearing any objections, so I'll go on to the last way we tell rocks apart. So another really important distinction is, are there layers? Layers are important. So we already talked a lot about layers in sedimentary rocks, like all of the geologic time and relative age stuff comes from layers in sedimentary rocks. And that's how they form. They form by stuff piling up and getting stuck together. That's how all sedimentary rocks, well, most of them, except for the evaporation ones, that's how they all form. But you can get layers in other kinds of rocks. So with igneous rocks, lava flows are layers. You'll get one lava flow and then another lava flow forms on top of it and hardens, and then another lava flow forms on top of it and hardens. So in this case, so this is Iceland, and you can see there's layers and layers of rock. But these are all volcanic rock. These are all sediment. These are all volcanic eruptions, different eruptions at different times. And you can do some of the layer-based detective work with this stuff as well, but it often doesn't work as well as sedimentary rocks, just because they form in kind of the same way all the time and cool at different rates depending on what was coming out of the volcano. There's just more variables. But perhaps most complicatedly is that metamorphic rocks can develop layers. Now, sometimes like you can have a sedimentary rock that turns into a metamorphic rock and it'll keep the layers it already had. But sometimes you can have a metamorphic rock that started as something that didn't have layers at all. But then because of the right conditions of pressure and temperature, the minerals might organize themselves into layers. So this thing, you can see this has layers, but it didn't form in layers. This developed layers because it was under a certain amount of pressure. And so this was probably granite originally. But then through a certain amount of pressure, all of the minerals sorted out into these layers. But the way that you get those layers and what's in them can tell you about how that happened. So you definitely wouldn't use this to tell time. All of this formed its layers at the same time. So it's not like in your sedimentary rock, this is going to be the oldest and this is going to be the youngest. Or in your layer of lava flows, this is going to be the oldest and this is going to be the youngest. This is all going to be the same age and just tell you about what happened to it. So does that make sense?
Yeah.
Again, don't worry too much about metamorphic rocks right now. They are the most complicated one, but by the time we get there, you'll know enough that it should hopefully be totally cool. But yeah. So those are our ways that you describe rocks, and different ones of these are going to come up more in different parts of the class. So just keep that in the back of your mind. It'll be back. The last thing for today is, so far we've talked a lot about, just earlier in this class and earlier today, talked about how the shape and arrangement of the continents changes over time. Plate tectonics is active and constantly changing. Things are moving and bumping into each other and moving apart and erupting and eroding, and things happen to rock. The Earth is a dynamic place. But when the plates change, when the tectonic setting changes, when something bumps into something, something erupts, something weathers away, rocks change too. So everything changes. And so, and it's not just like something turns into a metamorphic rock. Things can change from one kind of rock to another under certain conditions. And we call that the rock cycle. And so have any of you heard of this before? Okay, I'm seeing a few yeses in the chat. Seeing a couple of raised hands. Yeah. So the rock cycle, a few people haven't. Okay, so this is something, I mean, I know they mentioned this in like 4th grade for me, but I don't know if they still do. But the rock cycle, so the book definition is that it is the succession of events that results in transformation of earth materials from one rock type to another, and then another, and so on, and so on, and so on, and so on, rinse, wash, repeat. Basically what it says is that rocks can turn into other kinds of rocks. So even though we have our 3 categories, we have our igneous, sedimentary, and metamorphic, there are always things that can happen that can turn one into another. And so even though like metamorphic has the name like it has metamorphosis in the name, it implies change, really every kind of rock, or at least most kinds of rock, used to be some other kind of rock. Or like any type of rock has the potential to have been some other kind of rock. And just different conditions lead to that happening. So the rock cycle is often drawn as a thing that looks like this. And basically says, so every rock can become a different kind of rock or can become itself again. So like an igneous rock, all something has to do to become an igneous rock is melt and then re-solidify. So you can have something that starts as an igneous rock, and then it can harden and melt again, and it becomes an igneous rock again. But let's say that igneous rock hardens, and then it erodes away, and then the water takes that eroded particle and dumps it somewhere else where it gets stuck together. Then it's become a sedimentary rock. It started as an igneous rock, and now it's sedimentary. Or let's say you have that igneous rock, and it either gets buried by other stuff, or let's say it never erupted out of the volcano and just stayed inside the earth. And then let's say that gets buried more, or squished, or heated more. Then over time, that rock might turn into a metamorphic rock because it just takes temperature and pressure to turn something into a metamorphic rock. So an igneous rock can be igneous again, become sedimentary, or become metamorphic. So now let's say you have a sedimentary rock. It forms by things eroding and piling up and getting stuck together. So you can have that somewhere, and it can erode and move somewhere else and pile up somewhere else and become a different kind of sedimentary rock. So that can happen over and over again. Sedimentary rocks can become other sedimentary rocks. But let's say that that sedimentary rock gets somewhere hot enough that it melts. Then when it hardens again, it becomes an igneous rock. Or let's say again that that sedimentary rock gets buried deep enough or runs into a plate boundary that it gets under enough pressure that it starts to turn into something else. It doesn't melt, it just transforms into a metamorphic rock. So that's how a sedimentary rock can become the other two kinds of rock as well as itself again. And then lastly, again, metamorphic rocks form under heat and pressure, but not enough heat to melt them. And so you can have a metamorphic rock that gets heated and pressurized, and then it comes to the surface of the earth. And then something can happen where it gets heated and pressurized again. It can get covered by something, or it can end up in a different collision. It can end up in all kinds of things that rebury it and reheat it. And so a metamorphic rock can absolutely turn into a different kind of metamorphic rock. But let's say then that it gets super hot and it melts, then as soon as it resolidifies from melting, it's become an igneous rock. Or let's say that that rock, it comes up into, you get a lot of metamorphic rock in really big mountains. Let's say those mountains start to erode, and let's say the water carries that eroded material away and piles it up somewhere. Then eventually that bits of metamorphic rock can become a sedimentary rock. So I know I just said a lot of things at once, but basically every rock can become every other kind of rock. And that's the rock cycle. So sometimes you can have something that just goes back and forth between two kinds of rock. Sometimes you can have something that just becomes the same thing over and over. Sometimes you can have material that goes through the whole cycle. It varies. It changes with what plate tectonics is doing at the time, with what is where at a given time. It changes sometimes with the climate. There's a lot of factors that control this, but it is a cycle. So does that make sense?
Yes.
And we are also going to keep coming back to this. So this is something I want to introduce now. But with every kind of rock I'm going to talk about, we're going to talk about sort of where it comes from and how it can tie into these other things. Although I guess with igneous less so, because it's got to melt to become an igneous rock. So we're kind of always going to talk about, igneous, we're not going to talk too much about the other ones. But by the time we talk about sedimentary and metamorphic, we're going to keep talking about what's happening in the cycle. So does anyone have any questions about this cycle? About how something becomes something or not? Then does anyone have any other questions about any of the stuff in the rocks and rock cycle stuff from today? Right on. So in that case, so there will be a quick quiz, just a one question one that's up right after this class. Then there's also another vocabulary matching for igneous rocks, which we're going to start talking about on Monday. With that, so if you want to go, you can go, but I am glad to talk about specific questions on the test for the next 15 minutes. So if anyone wants to ask about any specific questions, just now's your time. And if you don't want to do it here, just shoot me an email, come to office hours.
Thank you, Professor.
Have a good one. And I will, as soon as we're done and no one else is here, I will fix that one other question. I'm really sorry about hitting the wrong button on that one.
Thank you, Professor.
Thank you all. All right, yeah, have a good weekend, everyone. No, the bad joke's fine. It's fine. I wasn't, yeah. No, I definitely, I'm a person who hits the wrong button sometimes too. But luckily, it's actually a lot easier to fix it on Canvas than it is with a paper test. So it should just do it automatically when I change the answer, I think. Yeah. So do you two have questions? Israel and Romario, you got any questions? Or are you just AFK? We'll give you one more minute in case you were kind of zoned out but plan to ask some questions, but I will end it in a minute. All right, so I'm gonna end this. If you do want to ask me questions, just email me. I will get to them as soon as I can. So have a good one.